Hi everyone, and welcome to part 2 of this formal logic video series. In this session I'm going to be looking at truth tables. So I'm going to start off by looking at the meanings of the logical constants and giving those meanings in terms of truth tables. Then I'm going to move on to look at some truth tables for more complex formulas and the conventions with which we construct those truth tables. And then finally I'm going to look at how we can use truth tables to test for logical equivalence and validity. And along the way I'm going to go through several exercises so that we can see all that's going on in action. So first of all, let's look at the meanings of the logical constants. The tilde symbol that we saw in the previous session is commonly read as not, or as a negation. And we can draw a truth table to show the way that this symbol works, this logical constant works, what function it performs in formulas, and we'll use our meta variables again to do that, because we want this to apply to every well-formed formula. So if phi is a well-formed formula, let's draw our truth table. Phi can have two truth values. It could either be true or it could be false. And that's exhaustive. There's no, according to PL, there's no non-truth values of things. Things are either true or false. So if we use the negation function on phi, what does a tilde do here? What does a not do? Well, it just reverses the truth value. So our truth table for not phi will look like this: false, true. And that gives us the meaning of this symbol within our language. The logical constants in PL are functions. They perform a functional role, and their meaning is the functional role that they perform in affecting the truth values of formulas. So by using a truth table we can exhaustively give the meaning of each of these symbols. So here we've got the negation symbol just reverses the truth value. Now, as well as knowing the truth table for each of these symbols, I think it's important that we have in mind a rule by which they operate. So I'm going to say that the rule for the negation symbol is that it reverses truth value. So now it doesn't matter where this occurs. We don't need to have a particular setup table. We just know that if a particular formula is true and the negation is applied to it, it reverses the truth value. That's its function, so it will go to false, and if it was false then it will go to true. Okay, so let's move on to look at, so this is the caret symbol, and it's commonly translated as and. So let's again draw a truth table for this. So here we're going to need two variables. So we've got phi and psi. So in this left-hand column, we just list the different combinations of truth value that these two things can have. So in the first case we've got them both being true, in the second we've got the first one being true, the second being false, in the third we've got false then true, and then in the last one we've got false and false. And that exhausts all of the possibilities. That's what we're doing when we make a truth table, is we're looking at every conceivable combination of truth values for the constituent parts and seeing how that affects the overall truth or falsity of the formula. So our formula is going to be phi and psi, and the way that the AND operator works, as I'm sure you know, is that it's going to come out true only when both of the conjuncts are true. So we should say this is also called a conjunction. Okay, so true true is going to be true, true false is going to be false, false true is going to be false, and false false is going to be false. And again, I think it's good to have a rule for each of these. So the rule for this, just looking at the truth table, I'm going to say true only when true, true. Okay, so there's my shorthand for what's going on in the table. If both of the conjuncts are true, then the whole sentence is true. Okay, let's move on to vel. So this is or, and it's sometimes also called a disjunction. So we're going to need a similar truth table as we had before, phi and psi. And phi or psi. Okay, so the way that the or symbol works, or the disjunction is, it's true when we've got just one true. So if at least one is true, then it turns out true. So true, true is going to be true. True, false is going to be true. False, true is going to be true. And so that should be false, false. False, false is going to be false. So the rule for this, and I think we should pick out the one that's different. That's what we did here, right? We said true only when true, true. This is the kind of unique, the unique thing, right? All the rest are false. We've only got one true. Well, here we've got one false. So when is it false? Well, it's only false when false, false. Right, again, so this rule can be applied to any situation, any much larger truth table. We don't need to always apply it in the way that it appears here. We can just remember this rule. Okay, let's move on to the hook. So this is commonly read as if, then, or sometimes implies. And again, we're going to need two variables. So phi and psi, true, true, false, false. Okay, now the if-then symbol is sometimes a little counterintuitive at first. Truth table goes like this: true, true is true, true, false is false. Remember, this is imply, so we're saying phi implies psi, so if phi is true and psi is false, then it can't imply it. Then these are the two that are sometimes a bit counterintuitive. These both come out as true. So this is the material conditional. Maybe I should put that there as well. Material conditional. And that's just the way that this symbol operates in PL. So whether we think that maybe that's a bit odd to say that, if we say if phi then psi and they're both false, maybe we think that should be false. The way that the material conditional operates is in this way. This is what we're doing. We're stating its meaning within our language. So it may not line up exactly with English, but it certainly is very useful in PL, as we'll see later on. So the rule for this, well, again, let's pick out the one that's different, and we can say only false when true, false, as in when the antecedent of this conditional is true and the consequent is false. Okay, finally, this is usually read if and only if, and this is the biconditional. Not enough space, but biconditional. So again, we're going to need two symbols. And our truth table is going to look like this. True, false, false, true. So notice that the biconditional is true only when the truth values of its constituent parts match. So when we've got true, true, it comes out true. In these two middle cases where we've got a true and a false, so they're differing in truth value, it comes out false. And when it's false, false, it comes out true. So our rule for this can be only true when match. Okay, so only true when the constituent parts match up. So there are, think of these as rules or just statements of the meanings of the symbols that we're going to be using in PL. And learning these truth tables and the rules is just going to mean that we can now apply this to much larger formulas, make much larger truth tables, and see how the truth value of larger formulas is affected by the truth and falsity of their constituent atomic formulas. So let's move on to do a little bit of that, and then we'll talk about the conventions for drawing larger truth tables. Okay, so here's a ever so slightly longer formula than we've looked at before. So we've got A and B, or B. So we've got the disjunction of B and this bracket here, A and B. Now, we have to do the truth tables of longer formulas in a particular order. Every formula is going to have a main operator, and that's the operator that determines the truth value of the whole formula. Now it looks like here that's going to be this disjunction. Let's just point to that. And that's because it's going to be this column here. This has scope over this entire, the longer bracket. This is the operator of this larger bracket. This smaller, or this conjunction here, only has scope over this bracket. So it has much narrower scope, and in order to do this main operator, we're going to need to know the value of this first. We're going to need to have done this operation, because this is the disjunction of B and this bracket. So unless we know the value of this bracket, what this bracket means in each of these 4 situations, we're not going to be able to do the full truth table. We're not going to be able to work out the main operator's values. So let's do A and B first. Well, our rule for A and B was that it's only true when both are true. So just looking at A and B here, we're going to get true, false, false, false. Now that we've worked that out, what we're going to be doing is the disjunction of this column and B, right? Because we could even write our truth values for B under here, so we can see what we're doing more clearly. So here we're doing the disjunction of these 2 columns, right? So our rule for this disjunction was it's only false when both are false. So here we're going to get true, true, it's going to be true, false, false, that's going to be false, false, true is going to be true, and false, false is going to be false. So there is the meaning of this sentence in PL, given these in each of these 4 situations. When A and B are true, A and B or B is true. When A and B are true, then false, A and B or B is false. Yeah, and so on. Now let's look at quite a large formula. Now in this one, we're going to need to make things clearer, we're going to need to number our operations so we know what order we're going to do things in. In the example that we just looked at, that wasn't really necessary because there were only 2. It wasn't complex enough to do that. But a convention that we should introduce is numbering the operations that we're going to do. This is going to make it simpler for you doing the truth table, but also when you come to have somebody else look at your truth table, they're going to be able to assess how you've done it in a much easier way, just by having these numbers to see what order you've gone through it in. Now a convention for numbering is that we always start with the main operator being 1. Now the main operator of a formula is the one that has the widest scope, so the one that is the main operator of the largest bracket. Well, the largest bracket goes from here to here, and the operator in there is this biconditional. Right, this is a biconditional of this bracket and this bracket here. So this is going to be our operator number 1. And we always start with the main operator being 1, just so that 1 is always the main operator. We can always find the main operator just by looking for the number 1. It doesn't matter whether your formula's got 3 operations in it or 23, the main operator is always going to be number 1. So there's our first convention. The main operator is always number 1. So let's just write that number, main operator 1. Okay. Then what we do is we just need to go and number the rest of the operations that we're going to do. And we'll count up. So in order to do this, we need to know the value of this bracket and this larger bracket. So what are the main operators in there? Well, if this one, it's the and, so that can be number 2. We'll go to the left first. So there we go, we've got 2. There's nothing else to do in that bracket, so in this one we've got this, which is 3. Now here we've got negations. I'm going to treat negations as an operation for the purposes of this. Sometimes you can just not treat them as operation, just know that not A is going to be the reverse of these. But for now I'm going to treat them as an operation that we need to do. So in order to know the value of this bracket, we need to know the value of not A, so that's going to be 4, and we need to know the value of this bracket here, from here to here. So that's going. So this this conditional here is the operator of this bracket, so that's going to be my number 5. And then I need to know the value of not A and not B, so 6 and 7. So that gives me an order in which to do these operations. And when I'm doing this, I'm always going to work back to 1. Okay, so I'm going to start with 7. Now my rule for negation is that it reverses the truth value. So true is going to go to false, true, false, true. So that's my first one done. 6 is next. So not A is going to be false, false, true, true. Then I'm going to look at 5. And what I'm doing here, you could think of this as the conditional of if 6 then 7, right? We're looking at these two columns here. So our rule for the conditional is it's only false when it goes from true to false. So we've got false, false, well that's going to be true, false, true, that's going to be true, true, false, there's a false one, and true, true. Now once we've done that, once we've worked out the value of 5, we're no longer really interested in these. So we can maybe strike through them, or I'm just scribbling them out in yellow so that we can concentrate just on this column, because this is the important one now. We don't need to know the values of not A and not B anymore. We just need to know the value of this bracket for our next couple of operations. Okay, next operation is 4, so not A again, and that's going to be false, false, true, true. Just reversing the truth values in this column here. And now we've got the conditional of not A and this bracket. So the conditional of 4 and 5, if you want to think of it in that way. Right, so we've got 5 being this column, and 4 being this one. So in a way, what we're doing in doing operation 3 is if 4 then 5, right, where we've got false, false, true, true, and true, true, false, true. Okay, so how's that going to turn out? Well, our conditional again has this rule: if it goes true to false, then it's false. So false, true is going to be true, false, true is going to be true, true, false will be false, and true, true is going to be true. Right? And now again, I can just scribble out these lines. We're not really interested in those anymore. We're only interested in this one for the purposes of doing later operations. I'll just get rid of these lines so we can see that a bit more clearly. Okay, so there's operation 3. Now we need to do 2. We've got A and B. Our rule for A and B is true when both true. So true, true is going to be true. True, false, it's going to be false. False, true, it's going to be false. And false, false is false. Okay, so we're now in a position to do our main operator, number 1. because we know the value of 3 and we know the value of 2. So this is the biconditional of the values under 2 and the values under 3, if you like. Our rule for the biconditional was it's only true if they match. So true matches, so that's going to be true. False true is going to be false. False is going to be true. And false true is going to be false. Again, then we can just ignore these. So we now know that the meaning of this whole formula in each of these situations comes out as true, false, true, false. Okay, so it's easy as that. We just use the rules that we've got to mechanically apply them to formulas in this way. Okay, now let's move on and we'll look at even more. It's complicated in a different way. It's not quite as long a formula, but we've got much more in the way of variables of sentence letters that can vary in truth value. So here's where we can look at another convention. So when we're drawing up the left-hand column of our truth table, so far we've only had 2 different sentence letters. So we've gone true, false in the far right column, and then true, false, and that exhausts the different possible combinations. When we get 4, there's a convention so that we get out all of the possibilities in the same way in each case. Right, this is just the way that logicians tend to draw truth tables. It's the way that everybody does it, so it's a good convention to pick up. It makes it far easier to read the truth table if you know that everyone's doing it in the same way. So if we just wrote out our first, that's wrong way around, true, false, true, false, true, false, false. So this 4, these here are really just what we had here, with just 2 possibilities. But now we've got 4 different sentence letters. We're going to need to add more rows because there's more possible combinations. Now what you can imagine that you're doing is just, when you add another one, you copy and paste, you copy the table here to below, and then you add on the left hand side for the first half, the first load of that we've, the part we copied is all going to be true, and then for the second it's all going to be false. Or another way of saying that is that the frequency with which we alternate between true and false doubles every step left we go in this left-hand table. So in the furthest right column it alternates every 1, true, false, and so on. When we go across, it goes every 2, true, false, and then every 4, true. And as you can probably guess, for the final column, I'm going to do exactly the same. So I'm just copying and pasting these columns here. But then under A, we're going to have, because we had 4 trues and then 4 falses here, we're going to have 8. Right? So true. And then 8 falses. Okay, so again, just to reiterate, I'll write this down, it is important to remember. The frequency with which true and false alternate doubles as we move left. Okay, so just remember that in your furthest right column it's going to be alternating every 1, and then just double it every time you move left. And use this convention for writing all of your truth tables. It makes things much more simple as we look at complex tables like this. Okay, but the same process is now going to be used on this more complicated truth table as we saw before. So we start off by working out which operator is going to be our main one. Well, it's the one that has scope over the largest bracket, so it's this conjunction. Then it doesn't really matter which one of these we do next. I'm going to just use a convention of going for the left one first all the time, so we'll go 2 and then 3. you could have done it the other way around. It wouldn't really matter in this case. Okay, so let's go through our operations then. So C and D, we know our rule for conjunction is true only when both true, so we're looking at just these two columns here, and that's going to be true, false, 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 true, false, 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 true, false, 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 true, false, false, false. Okay, so this table is a lot longer. In fact, let's just highlight the trues just to make things a bit easier on this much bigger table. Like that. It is easy to get lost in large truth tables, so give yourself enough space, and you can see that I've got a grid on here so that I can keep things all in line. You know, when you're writing your truth tables, feel free to use lined paper, use the lines, make a grid if you want, just to keep things neat. Okay, so next we've got to do A and B, so we're just looking at these two columns here, so that's going to be true, 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 false, 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 all the rest are false. False, false, false. And again, I'm just going to highlight the ones that are true, just so we can see where they are. Okay, so now that we've done 3 and 2, we're in a position to do our main operator, number 1, and again, we're just going to apply exactly the same rule. It's going to be much easier here because we can just see that the only place in which we've got these two highlighted T's is the top row. So again, use a different colour. So it's true in the first case, but it's false in every other. And doing a truth table is really as simple as that. Just applying those rules for each of the logical constants in this order, right? So we sort out our ordering first, and then we just apply our rules, and that's it. That's as easy as it is. Okay, another thing to just recap from what you will have done in critical thinking, just so we remember this. So here are some very basic truth tables just to pick out something that we can learn from looking at the truth table of a particular formula. So here we've got A or not A. Well, we know how to apply the negation rule. If we go through it in order, we're going to say this is the main operator, right? The or, and the negation is the subordinate to this disjunction. So the negation is going to turn out to be false, true, and then we're just going to do A or what's in column 2, right, or what's under not A. So true, false, according to this junction, it's true. It's only false when they're both false, so true, false is going to be true, and false, true is going to be true. So when we've got all trues under the column, in the column underneath our main operator, we're going to say that that formula is a tautology. Right, it's true by definition. It's true in virtue just of its meaning. There's no possible situation in which this could turn out to be false. It's always going to be true, just by virtue of, and you can see that just by thinking about it, right? A or not A. That has to be true in every case. Okay, let's have a look at the next one. A and not A. Again, order of our operations. This is going to be the main operator. Then the negation is subordinate to it. So we do the negation first. False, true. And then the rule for and is true when they're both true. So true, false is going to be false, and false, true is going to be false. So here we've got all falses in the column underneath our main operator. We'll call any formula like that a contradiction. Yeah, because there's no possible scenario in which it can turn out to be true. It's false by virtue of its very meaning. Then finally, looking at this one, again, let's work out our order of operations first. We're going to have to do, this is our main operator, right? It has the widest scope, and then it's this one here in these brackets. So we'll do number 2 first. A and B is going to be true, false, 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 and then we're doing A, then whatever's in this bracket, right? So A then 2, if you like to think of it in that way. So true, true is going to be true, true, false is going to be false, false, false is going to be true, and false, false is going to be true. So here, in this final bracket, we have some trues. Right, we've got 3 trues, but we've also got 1 false. So we'll say of any formula, if it has both truths, both true and false in the column under its main operator, that it is a contingency. And what does that mean? Well, it means that the truth of the formula overall is contingent in some way on the truth or falsity of its constituent parts. It's not true by definition, and it's not false by definition. It's true by virtue of the truth and falsity of its constituent parts. Okay, so let's move on a little bit to some of the uses of truth tables, beyond just showing that something is true by definition, or false by definition, or contingent on the truth values, as we've just seen there, of its constituent parts. We can also look at whether particular formulas in PL are logically equivalent. So, these aren't joined up in any way. In fact, we could maybe draw just a little line here to show that they're different formulas. They're being treated separately. Only one operation in here, so that's going to be our number 1. This one, 1, then 2. So if we do this first one, A or B, that's going to come out as true, 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 false. In this one we've got a not B to do, so that's going to come false, true, false, true, and then not B, then A. Well, false, true is true, true, true is true, false, false is true, true, false is false. Okay, and again I'm just going to scribble out that one there. And what we can see here is that these two columns are identical, right? The column underneath the main operator of A or B, true, 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 false, and under not B, then A, also true, 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 false. So what we can see there is that these two formulas are truth functionally equivalent. And another way, I'll just get rid of that, another way to bring that out would be to use our biconditional. Right? The biconditional really means logical equivalence. If one thing is biconditional to another, it's logically equivalent. And the way, remember, our rule works for this is it's true when they both match. So true, true is going to be true, true, true is true, 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 and false, false is true. So the biconditional here shows that these two are logically equivalent. Right? This operation here. But it's actually more useful not to add in a biconditional there. It's worth noting that that's what the biconditional is showing, but it's more useful not to do that sometimes, because we can now add on the right hand side another formula and see if it's also truth functionally equivalent to these two. So let's take not A, then B. Okay, we've got not A to work out first. Our main operator is going to be the conditional, and that. So we'll do not A first, false, false, true, true, and then not A then B is going to go false, true is true, false, false is true, true, true is true, and true, false is false. Right, so I'll rub out that column there. Once again we can see that the truth values underneath the main operator are identical in all three cases. So what we've seen then is that all three of these are logically equivalent statements. They're truth functionally equivalent. There's no difference in the truth value. So according to PL, there's no real difference between using any one of them. They're interchangeable. So there's a usage of truth tables to show that particular sentences of PL are equivalent. And we can do that for longer formulas as well. So again, let's just draw a line here so that we can see that these are not being treated as one formula, they're being treated separately. A or B, again we'll just true, 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 false. We'll just work out that. Now what we need to do is do this as we have done longer formulas before. So we need to work out which operator is the main one. Well, it's going to be the one that ranges over this bracket. So it looks like it's this conjunction. In order to do this conjunction, we're going to need to know the value of this, but we're also going to need to know the negated value of this bracket. So our next operation is the negation, and then it's the conjunction in this bracket. And then we'll just work back from 4 to 1. So A and B is going to be true, false, false, false. Not A or B, A and B, sorry, is going to be false, true, true, true. A or B is true, 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 false. And then we've got a conjunction, so true, false is going to be false, true, true is going to be true, 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 and false. Let's just strike through those so we know we're not interested in them. Okay, so in this case, if we look at the two truth values, they don't match, right? This line here, we've got a true and a false. All the rest are the same, but due to this line, these aren't truth function equivalent statements. And some of you will have already noticed that what we're picking out here is the difference between a inclusive and an exclusive disjunction. So an inclusive disjunction, an inclusive OR, is true when both are true. Whereas this exclusive disjunction excludes that case where they're both true. So this is true only when one is true. Okay. Another use for truth tables is showing whether particular strings of formulas in argument form are deductively valid. Now I'm sure you will remember your definition for deductive validity from critical thinking. An argument is deductively valid if the truth of its premises would guarantee the truth of its conclusion. Now, when we were doing arguments before, we set them out in this standard form. So we had P1 might have been A, P2, A then B, and then we had this inference bar come across, and our conclusion might have been B. Now, this inference bar isn't going to work for us anymore, so we're going to introduce a new symbol, and that's this. This is called the semantic turnstile. And we're going to use this to replace the inference bar. Now, note again, like our meta variables, this is not a part of PL. Nonetheless, it can be used to say some interesting stuff about strings of formulas in PL. So where we'd had this written out in this way in standard form, we had A then B, therefore B. Using the semantic turnstile, what we'll do is write out the formulas like this. A then B. Let's put that in brackets as well. Turnstile B. Okay? And formulas written in this way are called a sequent. Again, let's write that. So that's all of this. String of formulas in that way, arranged in an argument format. And what we can do is use a truth table in order to determine whether that sequent is deductively valid. So, just as we did above, we're going to treat these all as separate formulas. We're not going to try and do any kind of connectives between them. But what we need to do is work out the truth values for each premise. So A is just going to be its values there, true, true, false, false. A then B, well, that's going to be true, false, true, true, and B is true, false, true, false. Okay, now our rule for when something is deductively valid is just that the truth of its premises would guarantee the truth of its conclusion. So what we need to do is look at this truth table for along each of these rows and see whether there's any rows in which both of the premises are true, and then see whether the conclusion is also true. Well, look, this first one got 2 true premises, true, false, false, true, false, true. So this is the only case in which both of the premises are true. So we're looking at, what we said about deductive validity is it's, hypothetically speaking, if the premises are true, would the conclusion be true? And that's what we're doing. We're considering that situation. Both of the premises are true. Well, look, there we are, the conclusion is true. So this is deductively valid. And it's as simple as that to test for it with a truth table. Let's look at a slightly more complicated one. So again, we've got this might have been written out A, then B or C, not B, therefore C. And what we're going to do is just do the same thing again. We're going to, so A, our truth value is already here, true, 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 true. All the rest false. Now we're going to have to do a little bit of truth tabling, the kind of mechanistic rule application that we saw before. A, then B or C. Well, this is the main operator of that. So that'll be second. So we'll do B or C first. The rule for disjunction is only false when both false, so true, true is going to be true, true, false is going to be true, false, true is going to be true, false, 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 true, 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 false. And then we need to work out this conditional, so it's going to be a conditional of A and this bracket, so that's going to go true, true, is true, 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 and false. It's going to make that one false, false, true, it's going to be true, 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 and true. Okay, and then I'm just going to scribble out that one because, again, we're not interested in that. This column represents the truth value of this premise, right? A, then B or C. Okay, then we just need to do this operation for not B, so false, false, true, true, false, false, true, true, and then again, oh sorry, and we also need to do C, so that's just true, false, true, false, true, false, true, false, and then again what we need to do is look along each of these to see if there's any, or look at any and all situations in which all 3 of these premises are true. So we've got true, true, false, that's not going to work, true, true, false, true, 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 so this one is one that we're going to need to look at. True, false, true, false, true, false, false, true, false, false, true, true, false, true, true. Okay, so there's only one situation, and in that one, all 3 premises are true, and the conclusion's true. So again, this is deductively valid. Okay. Let's look at another example of doing that. So far we've seen that these are all deductively valid. Let's look at another one. So here we've got, this could be written out, A, then B, I'll bracket that as well up there, A, then B, not A, turnstile, not B. Okay, same again. So A, then B is going to be true, true, false, true, true, not A, false, false, true, true, and not B is false, true, false, true. Again, all we need to do now is just look, true, false, 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 true, 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 true. So here's 2 cases in which the premises are both true, but in this case, although in this bottom case we've got true, true, and true, we have got a situation in which we've got both premises being true, but the conclusion being false. Okay, so that's not deductively valid. In order for a truth table to show that a sequence is deductively valid, it needs to be that in every case in which the premises are true, the conclusion is also true. Because if we remember, our definition for validity is that the truth of the premises would guarantee the truth of the conclusion. And it's clear here that the truth of the premises don't guarantee the truth of the conclusion, because here we've got both being true and the conclusion being false, and here we've got both being true and the conclusion being true. So the truth or falsity of not B, the conclusion, is in some way independent of the truth and falsity of the premises. So that's not deductively valid. Okay, one final thing to look at is sometimes we'll see things written like this. So we've just got the turnstile with no premises on the left-hand side of it, just a conclusion. And we can read this as, it is a logical truth that not A and not A. So if you see, say you see this, you can read that as, it is a logical truth that phi. Okay, and this is going to be used when we've got, usually it's going to be tautological statements. Right, so because we've already seen that, if we do this, we're going to have that's the main operator, then that, then that. Not A is false, true. A and not A is false, false. So the negation of false, false is going to be true, true. So this sentence is a tautology. And in that sense, it's true just by virtue of its meaning. So it's a logical truth that not A and not A. So we'll use that sometimes just to express that.